Okay, so now we're going to be starting to discuss our main interest, which is radial quantization. Good. Okay. For simplicity, so this is just to illustrate the ideas in the simplest possible setting, let's work in D is equal to 2 Euclidean space. We could do this in any number of dimensions. We're just choosing D is equal to 2 to simplify the discussion as much as possible, seeing as it's the first time that we are doing radial quantization. The metric, well, we've got ds squared. It will be dx1 squared plus, let's make that a superscript, plus dx2 squared. Good. And let's just draw a picture of our plane. There we go. Here's x1. There is x2. Good. And the first thing that I'm going to do is just change coordinates, okay? And so I'm going to change coordinates. And in fact, this is a change of coordinates that you will have done many, many times in your life. So let's take x1 to be r cosine theta and x2 to be r sine theta. So we're swapping x1 and x2 for a radius and an angle. And you know the inverse mapping. It's just r1 is equal to x1 squared plus x2 squared square rooted. And tan theta is equal to x2 divided by x1. So that's the coordinate mapping and its inverse. And then what do we want to do? We want to do an equal r quantization. So we're now going to use surfaces of equal r to foliate our space. So here are a few equal r surfaces. To each such surface in classical physics, we would associate a phase space. If we were doing quantum mechanics, non-relativistic quantum mechanics, to each surface we would associate a Hilbert space. And in quantum field theory, to each surface we would associate a Fock space. If we look at a scaling, what a scaling will do, it'll take r into lambda multiplied by r. And if we have lambda greater than 1, we can choose that. Then we'll actually scale from a smaller equal r surface to a bigger equal r surface. So scaling maps between slices or leaves of our foliation. So now it's scaling, not time evolution that moves us between the different slices. And we know that scaling is generated by the dilatation operator D. So you can see that now D is playing the role that the Hamiltonian used to play. And this might look a little bit weird. We're relating circles of different lengths by the dilatation operator. Well, we can make things look a little bit more natural by doing a conformal transformation. So let's do that now. We're going to do two things. First, we're going to do a change of coordinates. And then we'll do a conformal transformation. And after we've done that, we'll get a much more natural picture of what's going on. Okay, so I'm going to start off, I'm going to rewrite my metric in terms of x1 and x2. And if you remember, what am I going to use? Something trivial here. If I look at dx1, well, I could get dr times by the cosine of theta. And then if I take d cosine theta, I'll get minus r sine theta d theta. I think you guys are absolutely comfortable with this. No problem at all here. And then plus r cosine theta d theta. So there's dx1 and dx2, and now I'm just going to plug it into this form for my metric and manipulate a little bit. I'm trusting that you guys know exactly how to do that. I don't think that is a big deal at all. If you do that successfully, you'll get ds squared is equal to dr squared plus r squared d theta squared. And this, of course, is still the metric of the plane, r2. I didn't do anything, okay? Now I'm going to do the change of coordinates that I wanted to do. I'm going to set r to be equal to e to the t. Then what do we know? Well, we know that dr will be equal to e to the t dt. We also know that r squared will be e to the 2t. So from the dr squared, I'm going to get an e to the 2t using the formula for dr. And from the r squared, I'll get an e to the 2t. So now, from my metric, I can pull up front an e to the 2t. From the dr squared, I'll be left with a dt squared. And from the r squared d theta squared, I'll be left just with d theta squared. Let me stress again that this is still R2 that we are discussing. We are now going to do a conformal transformation. So do conformal transformation. Now, let me just make a comment. If we were doing ordinary quantum field theory and I did a Lorentz transformation, you wouldn't bat an eyelid. Obviously, if I do a Lorentz transformation, none of the physics changes. I'm just looking at the physics from the point of view of a different inertial observer, the inertial observer associated with the boosted frame. That's a perfectly valid thing to do. In a conformal field theory, we are allowed to do a conformal transformation and none of the physics changes. So you shouldn't bat an eyelid at all. Thanks to conformal symmetry, if I do a conformal transformation, none of the physics will change. So this is a perfectly valid step to do. I'm still studying the same theory. I'll get the same answer for any physical question that I ask. I'll use the conformal transformation to swallow the e to the 2t sitting in front of the metric. So conformal transformations rescale the metric. So after the conformal transformation, I've got dt squared plus d theta squared. Now, look at this equation over here. R is equal to e to the t. So we know that R goes between 0 and infinity. When R is 0, t will be minus infinity. And when R is infinity, t is infinity. So we know that R runs from minus infinity to plus infinity. And we also know, we know this because we know all about angles, we know that theta lies between 0 and 2 pi. So if we look at this metric that we've got after doing the conformal transformation, well, as far as r goes, we've just got the real line. So this is for t, okay? And then as far as theta goes, we've got a circle, S1. That's for the theta coordinate. So now we're on the space r times S1. What is r times S1? That is the cylinder. So we've mapped from our plane to the cylinder. Now, some of you that are familiar with topology, you might feel a little queasy because you might tell me, well, hang on, the cylinder has got a different topology to the plane. That's absolutely true, okay? So for example, if I draw this path over here on the cylinder, I cannot deform this closed path to a point, whereas you'll tell me that on the plane, let me draw it in red again, you'll tell me that on the plane, any blue path that I draw, so the image of that blue path would be something like this. You'll tell me that any blue path that I draw can always be deformed to a point. So that shows you the topology of the two spaces are different. Actually, that's true. What the thing that we should be mapping from is the plane with a puncture in the middle. So there's a little pinprick in the middle, and that's not part of the space. So there's a little hole in the space. Now you can see that this blue part cannot be deformed to nothing. And in addition, usually we take the plane and we identify all points at infinity to get a sphere. Here you're not going to identify the points at infinity. So we would call this the two-punctured plane. There's a puncture at r is equal to naught, and there's a puncture at r is equal to infinity. There's a little hole there too. Those are not all the same point. And the two-punctured plane has exactly the same topology as the cylinder. So what we are mapping between is the cylinder and the two-punctured plane. Good. We'll continue in a moment.